supposed to be is about 40-45 minutes with 15 minutes for questions. So I'll take a pause around 15 or 20 minutes, maybe wait for 5 minutes, and then go ahead and then wait for something like that. Okay, good,
Sure.
good.
So I'll also be keeping a track of time, Milind. I'll give you a heads up when there is 30 minutes over, and then at 10 minutes.
Sounds good. So I'm ready to start whenever you are.
Yeah. So we'll just give a minute for, and then we'll get started.
Sure.
Okay, let's get started. Welcome everyone. Very good evening and morning to Milind. So we'll do the usual drill, unmute and say hi to Milind.
Hi,
Hello.
Milind.
Hi,
Hi.
Hello. Hi.
It's my pleasure to introduce Milind. He's the Director of AI for Social Good at Google Research India. He's also Gordon Mackay Professor of Computer Science and Director of Center for Research in Computation and Society at Harvard University. He has many awards to his fame, and recently he was awarded Distinguished Alumnus Award from BITS Pilani. We are lucky to have you here, Milind. So with that, we can get started.
All right. So I can't see your faces while I'm talking. I haven't figured that out yet, but I'll occasionally stop during the lecture and ask, wait for questions from you. So I'm absolutely thrilled that you're all here. And so in the interactions I had on Gather, one of the questions that was raised is, how do we get engaged in AI for social good research? So this is what I'll do. I'll explain with case studies how we engaged in particular projects in public health and conservation. So with the current progress in AI and my area of work, multi-agent systems, there's a clear opportunity now to direct these advances towards societal impact. We are focused on 3 areas: public health, conservation, and public safety and security. In all of these areas, viewing these societal problems via the lens of multi-agent systems, we are focused on the key research problems: how to optimize our limited intervention resources when interacting with other agents in these domains. So with respect to public health, the challenge is that we have limited number of social workers or public health officials. Concrete example is work we have done in homeless shelters in Los Angeles. Harnessing the social networks of homeless youth, we are able to show that our influence maximization algorithms that pick key influencers are far more effective in spreading HIV information amongst the homeless youth compared to traditional approaches. The technical area I'll discuss related to that is social networks and bandits. With respect to conservation, we have large conservation areas to protect limited number of ranger resources. Concrete example is work we've done in Uganda and Cambodia. Harnessing past poaching data, we are able to predict where poachers will set traps or snares. And for past several years, have been able to remove a large number of these snares, hundreds of thousands. The key example, the key technical area I'll focus on here is combining machine learning with game theory, so-called green security games. In the past, we have also worked on public safety and security, presenting a new model called Stackelberg security games and new algorithms based on this model that have been in use by security agencies in the United States, such as the Federal Air Marshals, to assign air marshals to flights. This is going on even today, or Coast Guard patrols, checkpoints at airports, and so forth. This is a topic I will not cover today since we have very limited time. Since taking over as the Director for AI for Social Good at Google Research Bangalore, we have launched several projects here in public health and conservation. I'll focus on one related to maternal and child care with an NGO called Arman, but there are several others as shown here, for example, in the area of conservation with Wildlife Conservation Trust, one of the projects we focused on is predicting where human-wildlife conflict will take place. So we can alert farmers before their crops get destroyed and try to intervene on that. But this is a very exciting area in terms of numbers of projects that we hope to launch in the future as well. So as you see all of these different projects, and I'll discuss some of them in more detail, there'll be three common themes that you should watch out for that cut across. First, the use of multi-agent systems research. This is my area of work, social networks, game theory, and so forth. And I'll introduce these topics as relevant during the presentation. Second, the use of a data to deployment pipeline. This work starts by immersing ourselves in the domain, trying to understand from the nonprofit that we usually engage with, what are their problems? What kind of data do they have? And having collected that data, the next step then is a predictive model. Given this amount of data, what do we predict to be high risk versus low risk cases? If we are doing work on helping TB patients, then which patients are high risk versus low risk? This is a prediction problem. Following that, we have a prescriptive algorithm. This is the intervention stage. So even though we may predict several cases to be high risk, we can't intervene on all of them because we have limited resources. So which cases should we intervene on? And that's where our multi-agent systems reasoning comes in. The final stage, which is equally important though, is field testing and deploying our work. It's very important that we field test and deploy because we want to understand whether our algorithms truly work in the field or not. But equally importantly, social impact is a key objective of the research. When we say AI for social good, we mean actually achieving social good in the field, not just writing papers about it. And one of the other things you'll see cutting across is the lack of data. We are supposed to be swimming in tons and tons of data, but in many of these social good domains, the challenge is that we really have very limited data. And so dealing with this data must be part of our project strategy. The third point that you will see in all of this work is work with non-governmental organizations, with nonprofits. To that end, we have really patrolled with wildlife conservation organizations in Cambodia and Malaysia and so forth. We've really spent time in homeless shelters trying to understand problems that these shelters face. Or, in a recent work, for example, with the TB prevention in Mumbai, really trying to visit these ASHA workers, trying to understand what challenges they face in managing TB patients so that we understand firsthand what the problems are and work with them. And the solutions we deliver are to assist in the work that they actually do. And so this work is in collaboration, interdisciplinary collaboration with the non-governmental organizations. So as you listen to this presentation, there are three key takeaways I hope that you'll see from this presentation. First, what are some key problem types for AI for social good in public health and conservation? Second, what are some key AI research challenges? Now, I would like you to pay attention to the models because the details, once you understand what is going on, you can read in the paper. So even though there'll be some mathematical expressions and algorithmic details I'll cover, if you don't follow them, that's okay. You can read the papers later. The key is to understand what is the overall model with which this problem is being solved. And third, how do we actually launch projects in AI for social good? So I assume some of you are here to actually start this kind of work. And so how do we go about starting these projects? So that's a point I wish to cover as well. So with that introduction, let's launch into the real topic here. First is this area of public health. The first challenge I'll focus on is information dissemination and behavior change. And this is a topic where I'll address the use of social networks in spreading information. So I'll cover papers that we've written from 2017 to now. These have appeared in conferences like AMAS and AAA, NICHCA, and NeurIPS. I'll give references to these. And if you're interested, later on also you can email me. I'll also highlight the role of key PhD students and postdocs by putting up their pictures in the top right-hand corner so you can see who actually did the work, led the work. So let's start with the information dissemination. So why is this problem important? Let's look at a very concrete example. This is work that we did while I was in Los Angeles. Right outside our university, there would be camps of homeless youth or homeless people. And in Los Angeles, there's a very large population of homeless persons. There are 6,000 youth who experience homelessness every night. One of the big challenges that we face is preventing HIV amongst the homeless youth. The rates of HIV/AIDS is 10 times the rates of normal housed populations. And so homeless shelters try to run campaigns to spread information about HIV, to try to get the youth to reduce the risk of HIV risk behaviors. Now, they do this by recruiting peer leaders, people who may be more popular, educate them about HIV, and then expect them to talk to their friends and their friends to talk to their friends. And in this way, information will spread, because you can't talk to each of the 6,000 homeless youth by yourself, meaning the homeless shelter cannot. So this is the way in which they hope information will disseminate in the homeless youth population. Now, this is a very marginalized population, so they don't have Facebook accounts and so on and so forth. So all of the interaction we are talking about here is face-to-face interaction, people talking to each other face-to-face. So there are many other applications of the same technique, whether you talk about HIV prevention. This is work that we are doing in Bangalore with a nonprofit called Swasti. This is HIV prevention among sex workers. Making people aware about tuberculosis risk. This is something that we have talked with the city TB officer in Mumbai, for example. So there are many other applications where you have to educate a population about some kind of a public health challenge. So what is this problem? So if you look at it from an AI perspective, this problem is known as influence maximization in a social network. So the traditional way to view the problem is that you're given some kind of a social network as an input, which is a graph, who's connected to whom, who's friends with whom. And then you have to choose K peer leaders or influencers. We assume information spreads in this independent cascade model, and I'll explain what that is. The goal here is to maximize the expected number of influence nodes. So in our problem, maximize the expected number of homeless youth who are informed about HIV prevention. Or in the case of the work we're doing with Swasti, maximize the number of sex workers who are informed about HIV in Bangalore or surrounding areas. Now, let me talk a bit about independent cascade model. So we have a social network that's given to us. And supposing we choose this node A as a peer leader. The assumption here is that node A will interact with node B, adjacent node, with a probability of 0.4. So youth A will inform youth B about HIV with a probability of 0.4. And then B will talk to C with a probability of 0.4. And in this way, information will cascade through the network. So in the case of a full social network that's given to us, and if we are told that we have a budget of 5 nodes that we can recruit, then the problem is which 5 nodes do we select in the whole network, because we can only select 5, so as to maximize the spread of information in this network. And this is an NP-hard problem. And so once we select these youth, our social work colleagues will then educate these youth about HIV, not only in terms of reducing risky sex behaviors, but also not sharing needles and so forth, and also how to communicate this information to their friends, and their friends will then talk to their friends, and in this way information will spread in the network. So as we try to think about this problem in the context of youth experiencing homelessness, we have to understand this is where research challenges come about. So we are given a model like the influence maximization model. There's the real world problem of youth experiencing homelessness. And the big research problem is the lack of data and uncertainty. And we should treat this as a research challenge and not a bug. So I had a student who we were working with on suicide prevention. And so the idea was predicting which youth may show tendencies towards suicide, which is obviously a very complicated and important problem. And the student would keep complaining to me that the data he has is messy. It's not very clean. He can't run the machine learning algorithm out of the box. forgetting that that is the challenge. How do you deal with messy real world data or lack of data? Because that is what is true in the real world. Because these are very marginalized kinds of populations. We just don't have the kind of data that you would, clean data with millions and millions of records that you would get in a very clean setting. So what are the challenges here? There's uncertainty in propagation probability. So I told you, earlier model assumes the probability is known, 0.4. But in reality, we don't know that. Secondly, we don't have a one-shot problem. We have a multi-step problem. And so I'll explain what I mean by that. So you can't invite all of the youth all at once because we have limited capacity. So we invite a few at a time, and that leads to a multi-step problem. And finally, the social network itself is not known. So traditional influence maximization assumes that the social network is known, but in reality, we just don't know the social network. So we have to query individual youth to figure out what is their social network. But we can't query all of the youth. We can only query a small budget, a small number of youth to uncover the social network. So we do some intelligent sampling, and I'll discuss what I mean by that. So as I mentioned, focus on the key ideas as I explain what we have done. If there are mathematical details, you can read the papers later. That's not as crucial to understanding the presentation. So here, let's start with this uncertainty in real-world networks. Supposing we have a youth C who's informed about HIV prevention, then we, in the traditional model, assume that there's a probability of 0.4 that youth D, who's adjacent to youth C, will be informed. Now, in reality, when we started interacting with the homeless shelters and so forth, we understood, obviously, this probability is not known exactly. So how do you deal with this? So we can represent this as this probability not being known, but being drawn from some distribution. So we'll sample it from some distribution to estimate the probability. Of course, the mean of this distribution itself is not known. So we can say that the mean of the distribution lies in some uncertainty interval. And this is one way of representing uncertainty. There are other ways you could represent uncertainty over the social network in terms of propagation probabilities. Having represented the problem as one of, maximizing influence under uncertainty, question is, how do we solve this problem? So one way to do this is to consider this as a problem where our algorithm is playing a game against nature. So our algorithm is trying to select key peer leaders to spread information, maximally spread information, and nature is acting as an opponent to choose parameter settings that cause our algorithm to perform as worse as possible. And so in playing this game, we arrive at a strategy which is robust to whatever manipulations nature may do. Of course, nature is not actively acting against us. We are just assuming nature is doing so, and that way arriving at a more robust strategy. For those familiar with game theoretic reasoning, this is a zero-sum game against nature, and we are trying to arrive at a max-min strategy. But again, as I said, if you think about, for those who are not familiar, think about it as this game we are playing against nature in order to build a robust algorithm. So here's how this is supposed to work. We have this influencer trying to choose a policy. So first, it'll say, okay, choose these 5 youth. But nature may, along the columns are the strategies nature can play. Along the rows are the strategies the influencer can play in choosing which youth to select. And so nature can choose parameter settings to cause our policy to perform as worse as possible. And so this is a game. As for those who may be familiar with game theory, you can see that this is a 2x2 game. For those who are not, basically the first number is a payoff to the influencer. So 0.8 is the payoff to the influencer, and minus of 0.8 is a payoff to nature. So basically, in this particular case, we are doing better, but in other cases, we may do worse. So we may get a negative reward ourselves. Solving 2x2 games is easy, but of course, in reality, what we have is a game with trillions of strategies for the influencer, because you can imagine if you have 100 nodes, a graph of 100 nodes, and you have to choose 20 influencers, that's 100 choose 20. So that's a very large number. And nature can choose parameter settings from any value in the interval that's given to it. And so nature has a large number of parameter settings. So this becomes a massive, massive scale game where large number of strategies for the influencer, large number of strategies for nature. So basically large number of rows, large number of columns can't even represent this problem in computer memory. So how do you actually solve such games? So we solve these games by an iterative procedure. So we start with some randomly initialized strategies. And then there's an iterative process where basically this double oracle approach, influencer will give back a strategy, which is its best response. And nature will give back a strategy, which is its best response. So there's a way of incrementally growing this game until you converge. And the basic idea here is that you can converge to a strategy for the influencer, which you can arrive at without expanding the full game. So the game may have trillions of strategies for the influencer and nature, but you can solve it in expanding maybe 100 strategies on each side, or maybe even 20 strategies on each side. And so we can prove that this algorithm converges with approximation guarantees. So this is one way in which we can arrive at a robust strategy. The second problem is the fact that we have a multi-step policy. What I mean by that is, supposing we have to select 20 youth in this network. We can't select all 20 all at once because our homeless shelter has limited capacity. So we may only be able to bring in 4. So we say, we select 4 youth and say, you're the first ones, we'll educate about HIV. Unfortunately, these are youth under difficult circumstances. One of them may get arrested on the way. Another one may choose to decide unable to come, doesn't have money for the bus ticket, may send in a friend of his or hers to arrive instead. And so we may invite some 4, but the people who show up may be only 3, and they may not be exactly the 3 that we had invited. So when we choose the next 4, which are shown by these green dots, we have to understand which people showed up in the first round. So this is a problem of multi-step policies. So we have information about our history. Who did we invite and who was absent in time 1? Who did we invite and who was absent in time 2? And given this history, we have to choose who to invite in the next time step. And so the other problem we face, of course, is that we don't actually know the state of the network. We don't know who has got the information about HIV and who has not. This is a problem of planning under uncertainty, observation uncertainty, because we don't have full knowledge of the state. Some of you may be familiar with reinforcement learning, and so you may start imagining this as a reinforcement learning problem. But for those who are not familiar, this problem can be cast as a partially observable Markov decision problem. And those who are not familiar with MDPs or POMDPs, no worries. Basically, what this is a planning approach that allows us to come up with a policy. We are trying to sequentially select nodes. So the homeless shelter is going to ask 5 people to show up. The world will come back and say, well, instead of these 5 people, these other 3 people showed up. So we got this observation as to which peer leaders actually showed up. The POMDP policy is then going to say, okay, invite the next 5. And the network state is not known. We don't know who has got the information about HIV. And so POMDP is a way of coming up with these kinds of policies. The one problem we have with POMDPs, they're extremely slow to solve. So you can think of this black box POMDP solver where you give them a state of the network. Basically, you give them the network, you give them uncertainty over the propagation probabilities, and it's going to come back with a policy for you, a plan. So the problem is that this black box is going to run very, very slowly. So what can we do? One of the ideas here is that the social networks of homeless youth, and in general, you find social networks may have communities. Here, youth who play basketball together, youth who hang out on the beach together. These are different sub-communities within the larger homeless youth community. And so, because of that, we can divide up the network into smaller networks. So here's an example. So we looked at networks of homeless youth in Hollywood and Venice, 2 separate cities in Los Angeles. And you can see that when you divide up the network in smaller subgroups, in the Hollywood case, only 12% of the edges cross the community structure, which means that there's communities where are densely connected, and then across communities, there are very few connections. And in Venice, again, just about 18% of such connections exist. So what does that mean? We are going to take the graph, we are going to divide it up into smaller partitions, and then we are going to give the smaller partitions to the PalmDP, and it is going to give us who to select within each partition separately. So it's an adaptive policy, but we are running it on smaller networks. There's some further complications. I refer you to our AMAS 2018 paper in case you're interested in following up on that. The final problem, and I'll just mainly introduce the problem to you and not delve too much into the details of how we solved it, is the fact that the social network of homeless youth is not known. So you go to a homeless shelter, there are a number of homeless youth, you don't really know what is the homeless shelter. You can't ask our social work colleagues are willing to put in the work, but we can't ask them, hey, just figure this out. So we can only sample, let's say, 20% of the network. So we can go to about 20% of the youth and say, who are your friends? And in this way, get some idea of the social network. And so the question is, which 20% of these youth can we sample from? Because we don't have the time available or the money available to actually collect the full social network. So the input here is a set of nodes, which is all the homeless youth in the homeless shelter. And our job is to come up with a sampling algorithm given a query budget. Let's say we can only query 20 youth. And then output which youth we will use as influence maximizers, as key influencers. And we want to have the performance of this algorithm, even after sampling, to be the exact same as close as possible to knowing the full network. And so there is an algorithm that we have that samples nodes randomly and then estimates the size of the communities and then chooses seeds from largest K communities. I'm going to skip these details and get into how we actually did the experiments and then take a pause to get your questions. So this is an algorithm. This basically, I've talked to you about three things. Network sampling. So we don't have the full social network. We only sample a small portion of it. Following that, we choose key peer leaders, and we do that in a robust fashion by playing a game against nature and in a multi-step fashion because we can't select all of the youth all at once. So we call these peer leaders, say 5 youth, please come in today for an education session, but not all of them will show up, as I mentioned, and then based on who's present or absent, we choose the next 5 and so on. So first we did a pilot test to see how this algorithm actually performs in practice. We recruited 230 youth experiencing homelessness. And so there's the sampling healer, which only has a sampled network, doesn't have a full network. So this was worked with 60 youth. Remember that this actual work done with actual homeless youth in Los Angeles. This is not a simulation of any kind. Healer is the full version. So basically it knows the full network. Healer Plus also is a version of Healer, knows the full network. Degree centrality is the traditional approach. It knows the full network, and we bring in the nodes with the highest degree, the most popular nodes. We recruited, as you see, about 60 youth in each case. And then we selected 12 peer leaders in each case. And the question is, who is able to spread more information after a month? So you're going to bring in the 12 youth in multi-step fashion. You're going to educate them about HIV. And then at the end of the month, we are going to see in this particular group of youth who got informed about HIV. Did our algorithms do as good a job as what was done by the traditional method of degree centrality? And here's what we find. In this case, we are comparing these algorithms that have full knowledge of the network, Healer, Healer Plus, and degree centrality. With the AI algorithms, Healer and Healer Plus, 75% of the youth got informed about HIV. With degree centrality, only 25% got informed. So the AI algorithms are able to be far more effective in spreading HIV information. But this is knowing the full network. Would sampling of network do just as well? And here's the result. When we sampled using the sampling healer algorithm, the true algorithm that we actually want to use, 80% of the population got informed about HIV. It's slightly higher than knowing the full network. That's a little bit of a surprise. But this is a pilot test, so this is a small variance that might have happened. But you can see that essentially sampling a small network and then running our algorithms seems to be just as effective. So that's the algorithm we decided to deploy in our large-scale study. Now, our social work colleagues are interested in actual behavior change. They're not interested just in terms of who got informed. So we did a study of 800 homeless youth. This is a study that was just completed. As far as we know, this is the first large-scale application of influence maximization for public health. These kinds of algorithms, if you look at the literature, have not been used in practice. So there's lots and lots of papers over the last 2 decades, but not real actual deployment for public health. We did this study with our 3 homeless shelters in LA that we've been working with, My French Place, Los Angeles LGBT Center, and Safe Place for Youth.
Milind, sorry to interrupt. We have plenty of questions on chat box. Also, we are 30 minutes up.
So let me do this. Let me finish this couple slides. I'll take a pause and then we can take questions. Is that okay?
Yeah, let's do that.
Okay. Thank you, everybody, for your patience. So here's at the end of 1 month what happened in terms of reduction of risky behaviors with respect to HIV. Reduction in condomless anal sex with sampling healer, which is our algorithm, you can see that there's a 30% reduction. But with degree centrality or the control group, where there was no intervention run at all, no information spread at all, you can see that there is no change. So our algorithm is far more effective in spreading HIV information, in causing behavior change. At the end of 3 months, the degree centrality approach began to catch up, but it's still not quite as good. And spreading this information faster is important because this is a risk behavior, so faster we can get it to reduce, the better. And secondly, this is a dynamic community. People leave the community, so it's important that we spread the information faster. Similar result with respect to condomless vaginal sex, and again, we can see that the sampling healer algorithm performs significantly better than degree centrality or the control group. So I'm going to skip this video. A last bit on this before we stop for questions. More recently, with Professor Ravindran at IIT Madras at AMAS 2020, we presented a reinforcement learning approach to the same problem, where essentially you start with a small portion of the network, and the RL agent then learns a policy. It does so by choosing nodes to query, and based on the query, as long as the query budget is not exceeded, it will keep querying. And then finally, once the query budget is exceeded, it will run influence maximization to get a reward, and then learn a policy of how to choose which nodes to query. So in comparison to our algorithm, there is improvement. So this is basically showing there's a large room here, a lot of room here to do more research. So I'll stop here and take your questions at this point.
Should we like
so I can't hear this question, sorry.
Am I audible?
Yeah, I can hear you. Please go ahead.
Okay, so should we like take questions from the chat box, or should we go with the live questions first?
Whichever you please go.
Hi, Milind. Thank you for this amazing talk. So I have a question regarding the degree centrality and the sampling thing. So in the degree centrality, we did have the whole graph. Is that correct?
Correct.
So why was it that after 1 month there was not much spread in the degree one, and on the other hand, in the sampling one, we had a lot of spread as compared to?
Correct. So remember, this is about behavior change. This is not just about information spread. So essentially, you can think about it that our algorithm is able to reach a lot more people. So if you think about people who actually change behavior, there's a larger group of people from which to select who actually change behavior. Degree centrality is slower in spreading information. So, and it doesn't reach as many. And so therefore, the behavior change is slow to be adopted. Does that make sense? So basically in 1 month, you're able to reach a far larger group of people with our algorithm. And so if you see, if say 30% of a large group is going to change their behavior, then with our algorithm, you will just be able to see a lot more change compared to degree centrality, which just reaches a fewer number of people. So 30% of a fewer number of people is just going to be fewer people to be able to convert. So that's why you see the difference. Does that make sense?
Okay. Yeah.
Hey, Milind, so as you mentioned that the lack of data is a major problem when tackling such issues. So
Please go on.
yeah, so over the last year or two, there have been a lot of efforts from your end, from your lab at Harvard and from Google's side to tackle such problems, uh, working with NGOs and stuff. So as a part of these efforts, you must have collected a lot of data. So is there any effort or any plan in making this data available to public?
Certainly, I guess there are. So first of all, we haven't collected more data. It's just ideas here of clever sampling that allows us to get samples, right? We don't actually have tons of data. Even at the end, all we have is like samples of data and so on. So with respect to networks of homeless youth, that data we certainly are going to be able to publish. Some of the other data, such as some of the, at least the tools that we have been using, that we have made public. All the code is public, for example, that's published along with the papers. Some of the data, for example, I'll talk a bit about wildlife conservation. That is a bit difficult to share because that gives away where the government knows where the poaching incidents are happening, and they don't want the poachers to know what we know about them. And so that is sort of not to be shared. But all the code for sure, we have released, and would be happy to discuss, in a collaboration, what can be released and what not, and so forth.
Let's pick a question from the chat box. Rishabh, do you want to read out your question?
That was me right now.
Okay. Okay, let's Ashutosh.
Yeah, so my question is in the data collection in the propositional domain. So for example, if we talk about that Arman project, so in such kind of social problems, the response rate is very low. So the data you collect, the subset of data you have collected, so how do you ensure that it represents the whole population and not to induce some bias while learning on the ML model?
Correct. And in the social network problem that I mentioned, right, we are sampling from the graph, and we have to be sure that it's not a biased sample. So we aren't, say, for example, if it's men versus women, that we don't sample a lot more men than women. And so this is indeed ensuring fair sampling is indeed a major research challenge. And at this point, I don't know of work that actually achieves that. And so it's a very active area of research to understand how to actually engage in fair network sampling.
Okay. And I also want to know that on the field test, so after making the prototype, so what on the other side of end user faces challenges to the product, or like the human-centered AI or something? Like they can able to identify or understand the results or the feedback from the ML model or something.
Right. So it's certainly a very important problem. The homeless shelters will ask, why did you choose these youth? Why, this person doesn't seem like a good peer leader. Why would you choose them? And it's very interesting because sometimes the algorithm is able to find people who are maybe introverts, don't seem to be very popular, but they're strategically placed in the network to spread the information. And so this is something where we need to be able to explain what's going on, but doesn't mean necessarily that the human intuition is correct. And so this human agent collaboration is a very interesting point. Again, this is, as you know, an amazing area for future work. So far, some of this explanation has been done manually rather than in an automated fashion. Let me do this in the interest of time. Let me cover a little bit more, and then I'll take a stop again, and then we can again interact if that is okay. And I'll move a little bit faster so that we can kind of understand what's going on, if that's okay.
Sounds good, Milind.
So I just wanted to say that the way we launched this project, I know some of you are interested in launching similar projects, was a collaboration between ourselves, AI researchers, social work researchers, and homeless shelters. And so this started with me discussing the work with a social work professor, and we focused on the problem. So I didn't go to the professor saying, hey, I know game theory or I know reinforcement learning, let me use it, but rather asking him what is a problem that this professor is working on. And this was about spreading information about HIV. So how do we actually solve this problem? Okay, so we have to work on social networks. So it's a problem-centered approach rather than a solution-driven approach. And the only resource I had is as an academic at that point was, we'll provide AI expertise to you to improve your work. And so you could imagine in your own universities forming groups, either approaching your colleagues in areas like social work or going to nonprofits and just saying, we are AI experts, we can help you with machine learning, and try to launch projects as we did at that time here. So I'll talk about another problem, which is health program adherence. And here, the basic idea I'll focus on is passive monitoring of adherence via machine learning. There's a active monitoring via bandits. I'll see how much time we have to cover that. So this is work that was mentioned just now in terms of work that we are doing here at Google Research India. As you know, maternal and child care is a major issue. A woman dies in childbirth every 15 minutes in India. 4 of 10 children are too thin or short. And so there are many nonprofits that are working in this area. The one that we are working with is an NGO called Arman. Arman works with 18 million women in India. It has 160,000 health workers who are working with them. And so one of the programs that they have is called M-Mitra. So basic idea here is to give a weekly call to a new or expectant mother. So basically, it's a friendly 3-minute message delivered in the voice of the local ASHA worker that says, okay, you are in the 3rd month of pregnancy, you're in the 6th week of pregnancy, this is what you should expect, or enroll in this government program, or take these iron tablets, or whatever it is that needs to be delivered. And in randomized control trials, they have shown that women who listen to their messages, there are 150 messages overall over the pregnancy and then up to the child being 1 year old, that women who listen, actually there's improvement in their health of the baby, compared to those who don't listen to their messages. So one problem they face, however, is that even though they have 2.2 million women enrolled in their program and so forth, is that significant portion of the women will become low listeners or drop out of the program. And so our job in working with Arman is predict which beneficiaries, which women are likely to drop out, so that Arman can go to those women before they drop out and have them continue to listen to the messages. So how does this work? So imagine you have mom number 1. So she gets the phone call in week 1. She doesn't pick up her phone. But then on week 2, 3, 4, and 5, she listens to the phone call. Mom number 2, listens to the message in week 1, week 2, doesn't listen in week 3, picks up the phone in week 4, doesn't listen in week 5, and so on and so on. And you can imagine, hundreds of thousands of such records of who's listened to what phone calls. Now, it turns out that after a while, in this particular case, mom number 2 and 4 dropped out. But we don't know that by just looking at this pattern of Arman doesn't know that as to who's going to drop out or not. And so if they want to intervene, they are not sure among the hundreds of thousands of women that they interact with, who do we concentrate our attention to stop them from dropping out. If we can predict in advance that mom number 2 and 4 are the ones at the highest risk of drop off, then Arman can start calling them even before they drop out and have them continue to listen. So that's what we did. Again, this is work done with IIT Madras with Professor Ravindran. So using neural networks for prediction, using data from past phone calls of that record of who's listened to what phone calls, we are able to predict who's at high risk of drop-off. And so in a pilot test, looking at beneficiaries, women who had enrolled in November and December of 2019, we looked at whether our predictions of drop-off came true for January through April of 2020. And in this pilot test, we are able to show that we reached about 0.8 accuracy, F1 recall and precision. So it's a pretty good result. And so now this software has been delivered to Arman. They're actually using it to conduct interventions. And hopefully this will actually benefit the 300,000 beneficiaries who are enrolled in mMitra today. And we are looking at the results of those interventions and trying to and are able to see that indeed by predicting these high-risk women, we are able to intervene on them and keep them in the program. There's a similar problem related to tuberculosis. As you know, tuberculosis kills 500,000 people every year in India. 3 million people are infected. And one big problem is non-adherence to TB treatment. So a similar problem of adherence. So the way people act in this case to try to improve people's adherence to TB medicine, because if they don't take their medicine, it's not only a problem for themselves, it's also a problem for the community because of drug-resistant bacteria, is that they have this pill pack and that the back of the pill pack is a phone number. And it's a randomized phone number, so the patients don't know what the number is in advance. Every time they try to take the pill, there's a phone number. They're supposed to call that to say, hey, I took my pill today. By looking at who's been calling and who's not, a health worker gets to know who's adhering and who's not. So if somebody doesn't call for a few days, then they can intervene on that patient and say, hey, you got to take your pill. Maybe go to their home and say, hey, you're not been taking your medicine, you need to take your medicine. But of course, you can't send health workers to all of the TB patients' homes. So which patients should we focus on? And we want to know this before the patients actually drop off, before the patients stop taking their medicine, stop making phone calls. So to intervene before patient miss doses, we want to predict who are at high risk of drop-off. Can we predict this adherence risk purely from the phone call patterns, similar to what we just saw with Arman? So that's what we've done with the 15,000 patients and 1.5 million phone calls with Everwell. We can see that we are able to make better predictions than what was being done by Everwell using their simple rules that they had. So machine learning approach did much better. There's a lot of, again, I mentioned to you this issue of data. It almost seems like I was saying there's no data. Now it seems like there's a lot of data. Actually, our KDD 2019 paper shows you that there's a lot of challenges in working with this data. It's not like a clean cut data. There's a lot of work that needs to be done to figure out what data to use to actually make these predictions. So this data challenge is a common one across these AI for social good domains. So I will mention to you one other problem, which is active adherence monitoring, and then briefly mention wildlife conservation efforts, and then take a stop, and then we can go to questions. So I'm not going to go through how we solve this problem, but here's the problem. In Mumbai, when we went last time to the chief TB officer, the city TB officer, she told us that, hey, we've run out of those sleeves from which patients make phone calls. In other words, the patients are no longer calling. Our health workers are calling patients to get information about who's adhering and who's not. So here's an ASHA worker. She has 200 patients under her care. And she needs to figure out who's adhering to TB medicine and who's not. So the way she can do, out of 200, she can call maybe 5 or 10 patients a day. So she may call, in this case, 3 patients to say, hey, are you adhering to your TB medicine or not? And encourage adherence. What she may find out is that out of these 3, these 2 took their medicine, the last one didn't. Now she has to decide, who do you call the next day? Maybe you call these 3 patients now. And again, you find that patient number 4 didn't take their medicine, but other patients did. And in this way, you keep calling, trying to decide who to call every day, because you can't call everybody every day. So this is a problem where we want to maintain adherence in a large population where we can only call a few patients a day. this is a classic problem of restless bandits. So basically for bandits, as some of you may know, it's pulling an arm. So you can pull K arms, that is you can call K patients per day. And you have to choose which patients to call based on what you have seen from them. And the patients can change their behavior along the way. So some patient may be adhering, they may stop adhering, and so forth. And so this is a problem that is cast as a restless bandit. We have a NeurIPS submission on this. I'll be very happy to discuss this some more a little later on. So this is a more active adherence problem. So I will skip the details of this problem and say that our algorithm is shown to perform better than the baseline while sacrificing just a little bit in solution quality. So this work with Arman was launched as a part of 6 separate projects we launched at Google Research India. And the work with TB was done previous to that, but the work with Arman was part of the 6 projects via a workshop that was held at Google Research. So we invited NGOs, we invited professors from different universities, and then we did a matchmaking ceremony where we basically said this NGO works with this professor and create a project. And so this is how we started these projects. Each of the project got our funding, compute cycles, and of course, collaboration from us. So this is another model of how these projects get started. I'll spend 2 minutes on wildlife conservation, and then I'll open it up for further questions. So this is work that we have been doing in national parks around the world. This is Murchison Falls National Park in Uganda, which I visited. And there's wonderful wildlife there, actually roaming the national park, but there's traps or snares, thousands of them that get placed to maim and kill these animals. And so the question for us is, can we predict where rangers should look for these traps? So you can imagine something like a Queen Elizabeth National Park in Uganda is thousands and thousands of square kilometers. There's not enough rangers to travel everywhere and find snares. So where should they look? So we divide the park into 1 kilometer by 1 kilometer grid square. We have past poaching data, and we are trying to predict where the rangers should be sent. So we have data on distance to rivers and roads for each grid cell, area habitat, slope of the land, and things like that. And we are trying to predict the probability of finding a snare. There's some complication here that I'm going to skip over as to how we created the machine learning model here. We made predictions based on past data and said, well, our model works great in the lab, but that's not enough. We got to go in the field and check how the model actually works. So the first test was done in Uganda in 2016, where they told us, okay, can you tell us where in areas that we've not patrolled, where to find snares? So we showed them these 2 9 square kilometer areas that are shown here with green dots. And we said, you patrol there. You've not patrolled there in the past. That's where you patrol, and you're going to find new snares. So I'll take just 1 or 2 minutes. So basically, these rangers patrolled there, and they found, all kinds of. So basically, they found a poached elephant, and then the next day they found a whole elephant snare roll. So poachers were active in the area. They were killing elephants, but before they could kill a next set of elephants, we were able to remove a whole elephant snare roll, thus saving the lives of these elephants. We are also able to remove a large number of antelope snares. We've done extensive tests since then in Queen Elizabeth and Murchison Falls National Park, saying we are able to predict areas of high risk and differentiate them from areas of low risk, where you'll find less number of snares. And where we predicted high risk, indeed more snares were found. Where we predicted less risk, indeed less snares were found. This has pattern seen also in Cambodia. These are pictures from snares being found from these predictions. In fact, the number of snare captures jumped 5-fold in Cambodia. And here's Rohit Singh, head of WWF Zero poaching efforts, saying, I'm super excited. Let's get going with other countries too. And so in collaboration, Microsoft's AI for Earth and the SMART platform, which is used by parks around the world, we have made our software available to 800 national parks around the globe. There's extensive testing going on. So this is super exciting in terms of seeing this machine learning tool go across the globe. So I'm going to skip all this other work and just come to the main points I wanted to make. That I hope you took away key problem types. I hope you took away some of the AI research challenges, and I hope you understood how we launched projects in AI for social good. There's more that I wanted to cover, But I'm going to stop here in the interest of time and take your questions.
So we have just 5 minutes, and we may not be able to cover all the questions. Probably we can take 2 questions and close.
Sure, please.
Okay, if people can unmute and ask a question, we can take 2 more questions. Who wants to go next?
Hey, great lecture. So I was having a question, like in case of social network that the data we are that the data you are collecting. So how do you like collect the interlinking between the people, like who will connect with who, and like how do you manage to collect that kind of data?
So the way this works is you go to a homeless youth and you say, who are your top 5 friends? And so that gives you that youth's 5 connections, right? And so that's the way we collect data. And now you can imagine that, you go to a homeless shelter, there may be 100 youth there, something like that. And you're only allowed to ask, you cannot ask all 100 youth, who are your friends or something like that. You can only ask, let's say 10 youth or 15 youth this question, who are your friends? And then based on that, you estimate what is the overall network and then select who are the key influencers. That's the problem that we are solving. Does that make sense? So the idea is, how do you sample such a network intelligently?
Yeah, okay.
So then you do not model them as probabilistically. As you started in the start of the lecture, you told that we model them as probabilities,
Correct,
or rather
correct.
distributions from which we take a sample for the mean. So if you are asking people, then it's sort of one probability. Am I
No,
right? Or
so I ask, let's say you ask me, who are your top 5 people you interact with. So I may say it's this youth Ram, this Sham, whatever it is, 5 youth. All you know is that these are people I interact with. What you don't know is how frequently, what is the probability with which information will spread. So you still have to model the interaction probabilistically. All you know is that I interact with this youth. You still don't know how frequently or the probability with which information will spread. So we still need all of that.
So you sample the mean from say 0.3 to 7 as you showed in the slide, and then take it as the Gaussian distribution.
So we say we basically say the mean is between 0.3 to 0.7. We don't have any distribution, so we can't sample because all we know is that there is this interval, right? So you can't sample. So basically now what you do is you have to be robust to this uncertainty. So there's when you have this kind of interval uncertainty, you don't have any distributions. You can't quite sample. You just know that somewhere in there is a mean, and then there's a Gaussian around it, but we don't know what is the mean. So we have to be robust to that whatever that distribution is, if that makes sense. So you still have to go on, please.
No, go on. Yeah, sorry.
No, I'd rather take your question since we're limited in time. Please go on.
Yeah, sorry. I just had a quick question. So I was thinking that, the problem of influence, right? Like how many people are in contact with how many other people. I thought that was very strikingly similar to COVID contact tracing. So I was wondering if a similar approach, finding out that, here K would be given to you, like the top K would be the people who are already infected. So I think this could also be a way to, I think this current framework could support who all are highly likely to get infected in the future. And I don't know, that was just a thought that I had.
No, that sounds like a really interesting connection there. We haven't pursued that, but seems like a very, very good idea. We have worked a bit on active case finding for tuberculosis. And so there, somewhat similar ideas are used, but what you're saying is a different thread. We haven't pursued that.
Yeah, I think this can also help in finding people who are asymptomatic carriers.
Potentially. Yeah, this is with the COVID, a very new area. We've done some modeling for COVID, but our focus has been more on testing, trying to show that rapid testing, even if it's inaccurate, is actually better than, more accurate testing that requires us to wait. So that's what we've been focused on.
So Google is in this unique position where you can get location data anonymized from a lot of users, and also information about connections, what people search for, where people are. I mean, all of this might be really useful when you build maps. So figuring out who is connected to whom seems like a really distributed problem, and I feel this data is also useful. What are your thoughts on that?
Certainly. Now, we don't have easy access to it because of all the privacy concerns for sure. So I wanted to be clear about that. The populations, though, that we sometimes work with, whether it's youth experiencing homelessness or other kinds of marginalized populations, say the sex workers and so forth that we're working with here in Bangalore, we don't have that kind of data available. They don't have, I mean, in Los Angeles, the youth just don't have the phones so we can't, they're not conducting search. So it's just a very, they're in a very difficult situation. And so we don't have that kind of a data-rich setting from where we can extract data. And so this is one of the, please go on.
Sorry, my idea was more in terms of, say, COVID monitoring in urban areas, like building on what Soundarya said.
I was actually thinking that we could use this sort of model in marginalized communities where people don't generally use phones. So one way would be to like model, like for example, let's say the family members each get like 10 weight for the graph, and like say like friends get like 5 weight, and like maybe the grocery center owner gets like 3 weight or something. So if you don't have the data, I mean, if they don't have phones and you can't dynamically check who are they interacting with, then maybe data collection in terms of who are the relatives, friends, and people they're interacting with would be like a feasible model if they don't have phones on hand.
Correct. And I guess the way we do this, and I know we are running out of time, so I'll just answer briefly, is that for each person we sample, we estimate each node, we try to estimate the size of the community that they're in. And so then having estimated the sizes of the communities, then you figure out which top K communities to select. And so it's a, it becomes a very interesting problem. And then in the real world, when you actually want to deploy it, you have to sort of figure out what's the right strategy. And so one of the things we rely on there is this friendship paradox. So what you do is you call a random person, and then you say, who are your friends? They say, okay, Abe, these 5 people are my friends. You go to that friend and you say, who are your friends? And it turns out that that friend will be more popular than the youth, right? This is friendship paradox. And so this is the way in which you can get a lot of information. So you go to a person, say, who are your friends? Pick one of the random persons within that friends list, and you ask that person, and that person is far more popular than the first person you picked. That's just the friendship paradox at work. And so we exploit that in estimating the sizes of the community and selecting the right people. So I know, Amina, we are out of time. So
yeah, if you have any parting comments for the group, we would like to hear that.
Well, thank you all for listening to me. I really appreciated all of your questions. If there are other questions I have not answered, please feel free to email those to me. And really, I hope you find this interesting to apply AI, all of the knowledge you've learned, towards social good. And there's tons and tons of nonprofits doing really amazing work. And I'm sure you can find some people to work with for AI for social good.
Thank you, Milind. Let's all thank Milind for the insightful talk. It was lovely having you with us.
Thank you so much.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you, Milind.
Thank you.
Thank you, Milind.
Thank you.
So we'll see you all tomorrow. Thank you so much for joining.
Thank you.
Thank you.
Thanks.
Bye.
Mm.